Okay, so we're continuing on here on this worksheet. For number 3, it says, let the absolute value, remember those up and down lines mean absolute value, and inside of that absolute value we have two numbers, x plus y, and that equals c, where c is a real number. Remember, in Algebra 1, everything we deal with are real numbers. Real numbers are anything that isn't the square root of -1. Alright? So in here, c is just any random number. We're just picking variables. We want to determine the number of points that would be on the graph on the equation for each case. So we're just kind of thinking conceptually about this equation, this absolute value equation, and we're going to try to decide at these places on the graph how many points would show up. So if you remember, c less than 0, remember anything less than 0 is a negative number. So we're talking about like the negative side of the graph. So if we have a graph like this, c less than 0 are things, if you're talking about y, you're talking about c, it would be below here. If you're talking about x, it would be over here. It's in the negative section of the graph. So c less than 0, that means negative numbers. So this means negative numbers. So basically, they're asking me if I do the absolute value of any number that I plug in for x plus y, can I ever get a negative number for c? Now, this basically comes back to the definition of what absolute value means. Absolute value means that it's going to make the number positive. Whatever's inside of those brackets comes out positive. So if we have this x plus y and it's inside of the brackets, every single number that comes out of there, it doesn't matter what we pick. If we pick negative numbers for x and y, whether we get a negative number or not in there, every number that comes out is coming out positive because these absolute value signs are around it. So basically what that's saying is that we can never have any negative numbers for this equation. So on this case, there will be none or no points there. All right. At the point case 2, c equals to 0, they're asking you, can it ever equal 0? Can c ever equal 0 if we've got an absolute value equation? And the answer to that is yes, it can happen exactly once. There's only one time when c is equal to 0, and that's when both x and y are 0. All right? So if I plug in 0 for x and y, I'm going to get 0. The absolute value of 0 is 0. So this means that there is one and only one point in that section. All right? And then finally, c greater than 0 just means anything bigger than 0. This means positive numbers. So these are positive numbers. And they're asking me, can I ever have positive numbers if I plug numbers in for x and y? And the answer is yes, you will always have positive numbers for this equation. So basically any positive number you can think of is a possibility here. So whenever we have that, we can have bunches and bunches and bunches of positive numbers. In math, we say, well, there's an infinite amount of positive numbers there. So the answer here is that it's infinite or infinity. All right. Moving on to number 4. The population of Kaiser, West Virginia can be predicted by this expression, 7,025 times 1.035 to the x power. Remember, if you look where the variable is, the variable's in the exponent, and we call that an exponential function. All right, so this is exponential, and remember, and you don't need to know this for this problem, but exponential functions make that hockey stick shape. All right, they look like hockey sticks. They can either be increasing like that or decreasing like that. Remember, when they're increasing like that, we call that exponential growth. When they're decreasing like that or coming down, we call that exponential decay. All right. So x is the number of years since 1998. That's a key point. This means that in 1998, that's the initial point or the initial year they took the population. All right. So what does the value 7,025 represent in this equation? So notice this graph up here really doesn't have anything to do with the problem. You can look up here and you can kind of analyze this graph, but you don't need anything in this graph to answer this question. The base year is how many years since the initial year. Notice 2000 is 2 years away from 1998, so that's what they're putting here. 2002 is 4 years, and so on. And this is the population in these various years. But all we need to know here for an exponential function is what does that initial value represent? So if you remember, when we had exponential functions, they were of this form, right? y is equal to a times b to the x. And I said that a is always an initial value and that b is the growth factor. All right? So the number in front, whatever we're multiplying by, the one that doesn't have the exponent or the variable in it, that's what the initial value is. And that's true for all types of functions. Wherever the constant is, that's the initial value. All right, so in this thing, 7,025, that's the number in front. So that is the initial population of Kaiser, West Virginia at whatever year they started. So you can say the year was 1998. So that means that 7,025 is the population of Kaiser in 1998 because that's the initial year. Okay, so this would be your answer to this problem. Okay, so that's the front of the worksheet. We'll slide over here to the back, try to knock some of these out in this video. Number 5, the formula for finding the final velocity, and this is a physics equation. V can be found using this formula. V is equal to V0 plus AT, where V0 is the initial velocity, A is the acceleration, and T is the time. Solve the formula for acceleration. Just for the record, just because there are two V's in this problem does not mean that those are the same thing. The fact that this little zero, we call that a naught, we call this V naught or V initial. All right, the fact that there's a little zero subscript here means that this V is different from this. We could very much have called this some other letter. Let's say we called it X. All right, this X and V naught are just as different from V. X is just as different from V as V naught is from V. So just because they're using the same letter doesn't mean that they're the same variable. All right. So, but in terms of this, they want us to solve for the acceleration. And in the problem, they tell us that A is the acceleration. So we're solving this equation for A, which means we want to get A by itself on one side of the equal sign or the other. So the easiest way to do that would be to take that equation, V is equal to V naught plus AT. The easiest way, we're trying to get A by itself. I cannot touch this term on the right until I get rid of V naught. This is a positive V naught. So if I want to get rid of it, to undo that, we do a minus V naught. So we'll subtract V0 from both sides. Remember, I told you these are not like terms because this has a little subscript and this doesn't. So when we don't have like terms, we can't combine them. So we just tack it on to the left side there. This cancels because that's what we wanted to happen. And then it's AT. All right. So still, we don't have A by itself yet. We have this T to deal with. Remember, when there's no plus or minus between these two terms, that means they're being multiplied together. So this is A times T. To undo a times T, we can divide both sides by T. And remember, when you have more than one term over here, the T has to go into both of them, so we make the big line. So our answer to this problem is going to be V minus V naught divided by T. So that is the equation solved for the acceleration. All right. If you have any questions, bring them to class.